First things first, though, if you are new here, hello, 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 everybody. So today I'm just going to be covering the MD5 Collision Attack Lab offered on the SEEDLab platform. If you want a link to the actual assignment, you can find it in the description box. All right, so we're just going to go ahead and get started with this. So like I said before, I'm going to be doing the MD5 Collision Attack Lab. As you can see here, I have the actual lab pulled up with all of the tasks and stuff that I'm going to be going through. All right, let's go ahead and get into the first task. So the first task is asking us to just generate two different files with the same MD5 hash. Now, at the beginning of this lab here, it tells us that we'll be working with this MD5 collision generator here that they've already built for us, which is very, very helpful. So we don't actually have to make two different files of the same hash. We just have to provide the algorithm with a prefix, and then it will generate two different binary outputs that have the same hash. So let's go ahead and get into this. So where is my image? So image is over here. I'm going to go ahead and open my terminal. So the first thing I want to do is make this prefix file. And then I'm going to tell us there she blows, our prefix file. So I'm going to go ahead and echo, let's just say Kaity code there, and I'm going to go ahead and put that into our prefix file. Go ahead and cat prefix txt, and there she is in our file. So the first thing that we're going to do is go ahead and generate those binary files using the tool that they have provided for us. So we're going to do this O flag, which is our output. Oh, we're going to do this P flag first, sorry, not the O flag. P flag first for our prefix. So we're going to use our O flag where we're going to put out our output file. So we're going to do output1.bin, and then we're going to do output2.bin. Right. So we're going to use diff to check the difference between our two files. Put one, and then we have output two. Diff. Dun, dun, dun. They differ. So the binary between these two files differs, right? And we can use this command to output the binary for these actually. So I'm going to go ahead and wait. I'm assuming they're going to be pretty long. So go ahead and clear so we have more room on our screen. And I'm going to go ahead and XXT, and then I'm going to output one, output that, and then XST, and then I'm going to put output two. Right. As we can see here, so we have our hexadecimal version. Right, and then we have our character version of everything. So we have here is Kaity codes rocks, right, which is our prefix, and then we have a ton of zeros here. Right, I'm assuming that's padding, and we'll get into that next. And then I'm assuming this is our like P or Q value. So if you go back to this PDF again, and it tells you how our MD5 collision generator works, it has the prefix, which is for us going to be the Kaity codes rocks. And then it's going to be padding, and then it's going to be this P value or this Q value. So the next thing that we're going to do is find the MD5 sum. Now, one thing to note is when you find the MD5 hash value for a specific phrase or message, right, it's called a checksum. So it makes sense that the command for this would be called MD5 sum, right? And they are exactly the same. So we go to these questions, and it says if the length of our prefix is not a multiple of 64, what is going to happen? So the way the MD5 algorithm works is it takes an input. I have a picture pulled up here. So it takes an input. So whatever your input is, for us, our input message was with our prefix, which is Kaity codes rocks. Right, so this would be our copy of the input message, and then there's some padding, which is our padding is separated by this 1 bit here, and then these would be our padding bits. And then in the last 64 bits of our input before we put it into the MD5 hashing algorithm would be the length of the message in its 64-bit representation. And this entire kind of binary representation would be what would be put into our MD5 hashing algorithm, and that is what would be compressed into a 128-bit hash value. Basically, if our prefix is not like a multiple of 64, then it would make sense that we would have some type of padding to like pad the message, right? So we don't really have to guess on this one. We can actually just see what happens if our prefix file is a multiple of 64. And I'm going to show you how to do that. I'm going to make us another prefix file. I'm going to make a prefix one, txt, right? And then I'm going to go ahead and make this file. I'm going to be using a little bash trick. Okay. And if we cat our prefix 64 here, we see it 64 bits, and then we can also do lsl. And then we can do everything. It's txt file. And we see that this is, why is it 65? Go back up to this echo, and I'm going to just make this 63 and see if that helps. And go back up here, and ta-da! So we are going to go ahead and run our MD5 collision generator on both of these. So we have our prefix file 2 and then _1 dot, then just to make sure everything is uniform, we'll do that. That's run. So we're just going to come back here and we're going to do the same thing for our 64 bit 2 _ 4 dot bin. All righty. Now on the actual PDF file, they give us a tool that we can use to display the binary and the hex, and it's called bless. So I'm going to go ahead and use that. I know I used XXD before, but we're just going to go ahead and just look at everything with this bless. Just go out _1. Okay, so we see we have our prefix here, and then we have all of these zeros right up until this point. So this is Kaity. I'm guessing this is a space, and then it's CODES. And so we have all of these zeros here, and then I'm guessing this is like whatever the P or Q value is. So I'm going to go ahead and exit that. And we're going to open up and see what one of our bin files for 64-bit. And we see there are no zeros here. Coincidence? I think not. Okay. And then the third question is are the data 128 bytes generated by the MD5 causing completely different, or the two output files? Please identify all the bytes that are different. Let's look at the bytes. If I do XXD out. And then I do diff. Well, that's a little trick there that you could use to find the differences between them. Okay, so task 2 here is just saying, so you can read over this yourself, but basically it's just going over how MD5 is a kind of like a recursive hashing algorithm where it splits each message into blocks of the same size and compresses those blocks, and then for the initial block, it just compresses that, and then each iteration of the algorithm is just a compression function with whatever the current block is and the previous block, and then we use all of that to create a 128 bit output for that. And all it's saying here is that if you have a collision, basically, if you have a collision with the MD5 algorithm, then any string that you concatenate with the original input message will generate the same hash function, and that message will also have a collision with the MD5 algorithm. So, and they want us to demonstrate that by using the cat method. So we can go ahead and do that. And the first thing that I think we want to do is just to make a file. I'm just going to make Kaity. Oh, no. My bad, y'all. And I just put this in, I'm just gonna make it file one. Right. We're gonna have echo Kaity file one, and we're gonna have echo codes. And oh, which one called Kaity in 2. This is the easiest way I know of how to just generate a collision with the MD5 algorithm, is to have the messages actually be the same. So we can go ahead and look at this by doing MD5 sum, finding the checksum for each one of these files. So we're going to have file 1, right? And then we're going to do the same thing for file 2. And we can see they have the same exact checksums for the MD5 algorithm. And then all we have to do is literally make a file, and we're going to have it code. Right, and we're going to put that into file. Hopefully one of these is not bad. Okay, there we go. That should work. And then we're just going to change this to 2. So our t value in this case would be just be code. So we're going to MD5 sum. So I have the checksum for file 1. And then my MD5 sum file 2. And they should be the same thing, but both of those outputs should be different from the checksums for file 1 and file 2. So we can check file 1 again, so we can see that they are different hash values, right? MD5 sum 2. There we go. But those two are the same. So these two are the same, right? And they're different from these two because these two have the suffix of codes in there. Now we're on to task 3, right? So we have to generate 2 executable files with the same MD hash. Okay, so I want you to look at that. It says we have to generate 2 executable files. And it's saying it's giving us a C program. Okay, so I guess first things first, the requirement for this is that you have some familiarity with C. Yeah, just for those who don't know, in C, a char is 1 byte long. So it makes sense that in this diagram here that we have 2 nibbles in our hexadecimal. So for this section, we have to make executable files that have the same hash values. The thing I'm going to do is generate that file. So let me go ahead and clear. And remember, I think in task 1, we use this. So we have echo $, and we're going to insert the Python code here, back, print, and that. And we're just going to have 0x41 with a comma there. And we're going to do that, say 199 times because it's supposed to be 20 long. And we're going to go ahead and put that into like the out file, out.txt. Okay, after that, we're going to come over here to this, and we're going to take this program, the C program here, copy that. Let's go ahead and copy that. And then we're going to head over to our virtual machine, and we're going to use Vim here. I'm just going to call it task 3, task3.c. And we're going to go in here. insert, and we're gonna go ahead and paste. All right, I'm just gonna format a little bit, escape, do that, and then I'm gonna go ahead and insert, do that, escape, and save and exit. And then we are going to go ahead and cat our out file that we generated earlier, and I'm just going to highlight this and copy, and then we'll go back to RV for that. Go back in here, insert, and then we're just going to paste. I'm going to go ahead and clear. Now, the next part of this is generating an out file for our C program. And the way that we do that is using GCC. Now, if you're not familiar with that, I don't know if this has a manual for it. Yes, it does. Yay! Okay, so if you don't know what GCC is, I would suggest you go into your terminal and do man GCC and kind of read through this. But basically, it's just as it says, it's a C and a C++ compiler. So it will compile our .c file and create for us a executable file. So the flag that we are going to use is this .o flag to get an output file so that we can finish the rest of this task. So we're going to go GCC, and then we are going to take our program, which is task.c, and we're going to generate an out file, which we are going to go call task3.o. Okay, there we go. And then we can just check and see that this is actually in here. So it is, and now we can move on. Open our out file with bless. So we're going to go bless task 3.o. Now it'll be easy to find where our array is because it'll be a lot of A values. Down here you can see where the offset is. If you click on here, it converts from hexadecimal to a decimal and other things. So that's binary. That's the binary of where our start position for the array is. And this is the decimal form. So 4,160 bytes away from the start of the binary file. So yeah, we're going to go ahead and check and see if that is a multiple of 64, because from our explanation for task 3, we can see, let me see, I know somewhere it says, yeah, the length of the prefix needs to be a multiple of 64 bytes. So let's go ahead and check. So we 4,160, 160 divided by 64, and it's 65. Okay, cool beans. So I'm gonna go ahead and up this value. So let's just add 64 more bytes. What's that? 4224. So we're going to go ahead and take the first 4,224 bytes of our binary file, and we're going to save that as our prefix. We're going to go head -c, and we are going to take the first 4,224 bytes of our task 3 binary output file. And then we are going to input that into a prefix file. So there we go. So from task 1, we use this MD5 collision generator. So we're going to go ahead and use that so we can generate another hash value that's going to be the same as our prefix that we've already generated from our executable file. B.in. So we have that now, and we can just go ahead and check and see if those are here. So we can check and see our bin files, and they are right there. All right, so the next thing that I want to do is generate our suffix. And our suffix, if we look over at the PDF for this lab, give me one sec. So refuses to come up. So if we're looking at this, so we have the prefix, which is a multiple of 64, and we already know that we took the first about 4,200 bytes of our executable file here. And so we have a multiple of 64 bytes, right? And then we know we have this 128 byte region here. And then we're going to have the rest of our program, which is the suffix. So all we're going to do to generate our suffix is I'm just going to literally take this 4224 value that we have there and then add 128 to it. And now we have the number of byte offset that we need for our suffix, which is 4352. So I'm just going to generate our suffix using that number. Okay, so right now we have our prefix, we have our suffix, and we have our we basically have our P and our Q value from the MD5 collision generator that we have. We go back to our file here. So we have our prefix, we've isolated our prefix already, we've isolated our suffix already, and we use our MD5 collision generator to generate a P and Q value from our MD5 collision generator. Going back to the terminal, so we have our task3_a bin fold binary file, and then we have the B binary file. And then all we're going to do is just take the tail end of those. So, right, and then we're going to save that as our P value. And then we are going to do the same thing for B. We're going to concatenate everything together. So we have our prefix, we have our 128 byte region, which is our P, right, that we just got. And then we have our suffix, which we got from our executable. That. And then we're going to do the same thing for our Q value. Now we can see if the checksums are the same. 5. And we see here that the hash values indeed are the same, but let's make this a little bit more interesting and actually see what happens if we were to actually execute these. Actually try to execute these files. Boom. And we see, so we know that our file actually outputs what is in the array. Okay, I want to sort of recap what we've already learned from the previous 3 tasks. So in task 1, we were introduced to this MD5 collision generator where it generates 2 binaries that create the same hash. And those binaries are basically summed up with the same prefix file and some padding. The P and the Q value are completely different from each other. And then task 2 was to understand this property, was to understand the MD5 property with concatenation. And task 1 with the MD5 collision, we know that we have a P and a Q value that are two different values that are generated with our MD5 collision generator, right? We know those two are different, but they generate the same hash value. And we also know that if we were to concatenate a suffix or prefix, it would generate the same hash value as well. So in task 3, we kind of exploit that and we use it to generate 2 different executable files that have the same MD5 hash value. Now, task 4 here gives a very good explanation of how these types of collision attacks could apply to real world examples. It's basically just going to be the same steps that we used in the previous task. So in order to generate this file, so we have this little kind of like pseudo code for what we want to do. And then we have this picture here. So again, we want to generate the prefix, which is a multiple of 64 bytes. And then we will have the suffix, which is the rest of the program. So before we get started with this task 4 program here, I'm going to go up here since I made the terrible mistake of deleting all of my code from the previous task. I'm going to go ahead and copy this right? And then I'm going to come over here and just the task for, let's see, insert, come out of there. Cool. So GCC task, cool. And then let me just run this real quick to see if it's correct. Benign code. Cool. And then we just use black task for to find out where our array starts. Click 1040. Okay. The head. I'm going to take bytes and we're going to take the first 4160. So we generate the P and the Q with MD5 call. So now we just have to generate, we just have to get our P and Q value, right? And then we're going to isolate bytes, and then we're going to get the last 128 bytes. And then we're going to take the same thing and we're going to make a Q. So I'm just going to look back at this diagram that they provided for how they decided to, yeah, we're going to have to take off part of this suffix to insert the p-value I'm seeing here. So that should be simple. We can just use head and tail like we've been using before, but first we are going to check out our suffix. Okay, so here's our suffix. Okay, I'm guessing this is the latter part of our X array, and then this is the beginning of our Y array. So we want to insert the P value into the Y array. So I'm just going to mark where this Y array starts here, offset 97. So over here, the thing I'm going to do is isolate this section of the suffix first, and that should be a simple head command. So the first thing I'm going to do is go head, and then I'm going to take the first 97 fix part 1. So this is our suffix part 1 here that we have, and we want this part here. So I think I'm going to just go ahead and take 128 from that. So we have 97, and then our offset is 28. So that is 225 that I'm going to take. 225, and that is off of our suffix. And then this is going to be our suffix part. So this is where we start to piece everything together. I'm just going to call it task 4_1. Task 4_. Let's first look back over here. So basically what we've done is we've created our 2 executable files. I feel like this one should be benign and then this one should be malicious. Just looking at the picture. Let's go back to our terminal here, and I'm just going to chmod these and add executable to task 4_1. Right, and then I'm going to task. Malicious code.
What? A few moments later.
Why?
I'm thinking there's one too many A's in the suffix 1, and we're going to make that suffix. And then I'm going to take tail bytes, and I'm going to take the first 96 of suffix __1, and then I'm going to make that the suffix _1. thinking we're all good, and we're going to try this yet again. So we're going to cat our task 4_1 schma score 1. You see what happens when you actually understand what's going on? You can debug stuff and things start to make sense. Now I can just go ahead and change my second one, task 4_2, and then this one should be our malicious code. Task 4_, malicious code and benign code. All right, you guys, thank you so much for staying with me to the end. I hope that was very helpful for you guys. If you have literally any questions about the lab, feel free to ask me. I'll answer your questions down below. This is Kaity Codes. I hope to see you in my next video. Bye, y'all.